Let's just talk about drawing free body diagrams. Okay, so just a quick reminder here. So it says free body diagrams are diagrams used to show the relative magnitude and the direction of all forces acting upon an object in a given situation. So basically, it just shows the forces, right? Where's my thing? My highlighter thing?
It's okay, Mr. Mayor.
No, I want it.
Man, did I drop my pencil again?
Once again, a free body diagram shows all the forces. So it's a good way. It's a good way to start any question that involves forces, basically, right? Drawing that free body diagram gives you a visual, gives you an idea of what is going on. And I didn't go through that front page, did I? Should I do that first? Let's go through that front page first. I'll come back to that. Okay, so a free body diagram is a special example of the vector diagram discussed in an earlier unit. These diagrams will be used throughout our study of physics. The sides of the arrow in a free body diagram reflect the magnitude of the force. So generally, the longer the arrow, the greater the force, right?
Yes.
Generally. Yep. The direction of the arrow shows the direction the force is acting. Each force arrow in the diagram is labeled to indicate the exact type of force. It is generally customary in a free body diagram to represent the object by a box, so just a square, and to draw the force arrow from the center of the box outward in the direction that the force is acting. An example is shown for it. So generally, even though things might be pushed, we show them as a pull. It's just a convention. Okay, so in other words, like if this applied force was really a push, you wouldn't put it there as a push, you would put it there as a pull, because it really doesn't matter. It's showing that a force in that direction.
Yes.
Okay, that's all it's the same. There are some textbooks that don't use the box, they just use a very small dot, and it would just kind of look like that.
That's,
kind of.
yeah, that's
No, I prefer the box. I don't know why.
You have to have mass. You're not as fast as Tim Sharp. She's still fast.
So I don't have the high score in that game?
No.
Oh.
Miss Tim Sharp. She's got it down.
Wow.
Like she presses it before the thing's even there.
Wow, that's fast. Okay. Do I need to go through all this, do you think? I don't think so. You know what? How about you guys take, I think there's 11 questions, am I right? There's 11 questions. Why don't you guys take like about 5 minutes and just try those?
Because my thing's stapled backwards.
Is it? Try those, and then I'll give you the answers right away.
4 courses. I don't know.
I'll do the first 2, because they're on the first page of this one here. A book is at rest on a tabletop. Diagram the forces acting on the book. Okay? So here you got your book. You got the weight force or gravity down. And you got now, is it moving? Is it accelerating? In fact, the net force is 0, right? So these forces are balanced. What's the upward force called? Do you remember? Normal force, Fn. Normal force. I find the biggest problem that students have is they're not sure what to label it. Really, that's just a label for you. Okay? Weight force and normal force are pretty generic. After that, it's kind of up to you.
Huh.
A girl is suspended motionless from the ceiling by 2 ropes. Diagram the force is acting on the combination of girl and bar. Okay, so there's the box. Gravity down, Fw. Now, because there's 2, right? There's 2 ropes, so we would call it like F1 and F2 maybe. Or you could call it like FT, tension 1, tension 2. I also don't have a problem with just one force being up either. Really. Unless it asks for the individual amounts, right? Maybe it's probably better to be 2. Here's an interesting thing. I got an email from a student from last year. She's taking physics at the university, and she sent me this question. She said, "Can you solve this, Mr. Mann?" And I'm like, "No, I can't."
Did you try? Yes, you could try.
Well, this object here weighs 50 newtons. This object here weighs 40 newtons, and we have to find the tension in the 3 ropes, A, B, and C.
That's cool.
Now, normally, I can do this, but the problem is that I've got, and you're going to get to this, I got a Y component of A, I got a Y component of B, I got a Y component of C. So I got the Y components all add up to 50. It's 90.
Wow. Now we what you could do before, now we can go through.
The question is,
But I still can't solve it because I got 2 equations.
Be like awesome. What's it called? That janitor that's like right on. Goodwill Hunting.
Maybe.
Just a reminder that your recorder is on and going, so.
She came back to me and said it was really simple when she asked for prompts, but
You're recording.
what do you think about that? I just had an idea.
Not sure.
Hey? Well, it's component vectors is what it is.
Yeah, so you want to ask
But you will be able to do questions that are of the same genre, just simpler. Okay? Yep. Should I keep going? Or do you want to try some?
Well, let's try some more.
Pretty much done? Okay, I'll give you a couple minutes to try. Okay, so number 3. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it is falling. So you should have just gravity. It says neglect air resistance, which means don't include air resistance. So it's in free fall. Here we have a flying squirrel named Rocky. He's gliding from a tree to the ground at a constant velocity. Is that important?
Yes.
What does constant velocity mean? The forces are equal or balanced. Consider air resistance. So you've got weight force down, and you've got, now the air resistance, you can write it as F air if you want, or FF. It's really a friction force, really, right? But they would have to be equal and opposite. A rightward force applied to a book in order to move it across a desk with a rightward acceleration. So that means that there is a overall net force. Exactly. Consider friction, neglect air resistance. So the up and down, the Y components, right? The up and down are equal. That would be in the normal force. I apologize for the little tiny space there to write, eh?
Yeah.
It's lousy. The normal force. But now we got a rightward acceleration, so that means that my FA, what does FA stand for? I would call it applied force. The overall applied force would be greater than the friction force, right?
What is it there when it says neglect air resistance?
It means ignore air resistance. Well, if there was air resistance, then I guess there would be a small little bit of air resistance that way, right? Opposite the motion. As well as the friction, yep.
What's the... I'm so tired.
Number 6, we got the same book, but it's at a constant velocity. So all that means is what? The forces are equal. So FA or FW and FN, and you got an applied force and a friction force that are equivalent. And like, if they have to be equal, make them reasonably close to equal. I'm not going to get my ruler out and measure, but my eye should say, yeah, those are close enough to equal. Right? And if you're going to make it bigger, make sure it's bigger. Okay, college student rests a backpack upon his shoulder. Pack is suspended motions by one strap. Diagram the vertical forces. So you just got weight force, and I guess it's, if there's a rope or a strap on it, would be a tension, so it'd be FT. Okay? You've done all these questions already in grade 11. Remember this sheet?
Yep.
We never did tension.
No?
Oh, Megan knows everything.
Maybe you were stressed when we were doing tension. Yep, could be. Yep, if they're ropes, yep. Skydiver descending with a constant velocity, consider air resistance. So you got weight force. No, it's not normal force, it would be FF, a friction force, or F air, I guess. Something like that. A force applied to the right to drag a sled across loosely packed snow. Well, that's code for there's friction with a rightward acceleration. Weight force, normal force, friction force. This is going
that way.
Rightward acceleration, right? So FA, big FA. Ah, yes. And number 10, this is the one that there always fights break out. A football is moving upward towards its peak after having been booted. Neglect air resistance. So, of course, football happens on Earth, so we got the weight force. And that's it.
Yep.
There is no force up.
Because this is just momentum now.
Exactly right. After the football has been booted, or thrown,
Also, they're talking.
what force is acting on it?
Gravity.
Right? You weren't ready, but you got a good hand, so I threw it to you. After it's left off in hand, what's causing it to continue to move?
Momentum.
Momentum or inertia, right? If I apply a bigger force,
Inertia.
oh!
Oh, headshot.
I was trying to throw it at, I'm sorry. Good thing it's so small. Did I scare you? I'm sorry. I was trying to throw it at Jared. I guess I threw a curveball. I was trying to hit Jared in the head, not you. Sorry. If I apply a bigger force, it goes farther, right? But the diagram is still the same. You know,
Before you steal them, what?
the car is coasting to the right and slowing down. Neglect air resistance. So you would have,
No acceleration.
right, well, that's not true. You'd have the weight force down, you'd have the normal force of this, and it's slowing down, so it would be a friction force that would be slowing it down, right? So it would actually have a net force that would be slowing down. Okay, now, thank you for reminding me that I didn't do the find that page. So let's just briefly talk about what's coming up in this unit here. So, you are supposed to, by the end of the unit, be able to solve vector problems for objects in equilibrium, much like the one on the board.
Oh!
Okay? But easier than that. I'm looking at the front page now, Danielle. Solve vector problems for objects in equilibrium. What do you think equilibrium means?
Equal.
Yeah, you're on the right track. Calculate the forces acting on an object resting on an inclined plane. Calculate the components of F gravity exerted on an object resting on an inclined plane. Solve problems with friction for objects on a horizontal surface and on an inclined plane. What do they mean by an inclined plane, do you think?
Something going up.
Ramp.
Ramp.
Solve problems using F net equals ma, where F net is equal to F applied plus F friction, using kinematics equations from the previous unit. And perform an experiment to investigate force acting on an object. We will do that as well. Okay, so these are the problem types. You will see horizontal force with no friction, which is basically grade 11. So you got this one, no friction. You're going to have horizontal force with friction. Like that. Angled force with friction. Yeah. You've done most of them. Angled surface, no friction. Angled surface with friction.
This is like my least favorite.
And equilibrium, where the forces are all balanced. So Brett is right. You've done sort of beginner versions of almost all of them, with the exception of the ramp ones. You haven't really seen those, right? You have seen a little bit of this already. Yeah. You can expect to see at least one of each one of those type of problems on the test. Okay? So what I'm going to do is I'm going to do some sample questions for grade 11, and then I'm going to give you a little bit of time to work over it. We're going to get the time fairly quickly. So just to sort of remind you of some things from grade 11, how you should really get that here better. Question number 1. These are easy. An automobile has a mass of 1,600 kilograms. What force is required to give it an acceleration of 1.2 if there are frictional forces totaling 200 newtons? So let's draw our FBD.
Holy, I remember all of this.
Right? That's why I reviewed them. So we got a car, it's acting on Earth, we got weight force down, normal force up. Generally, unless the object is moving vertically, you can usually just not draw those. Like, it doesn't really come into play.
Cancel it out.
Cancel it out, just sort of ignore. What force is required to give it an acceleration of 1.2 if there are frictional forces totaling 200? So that tells me that there is an applied force, Fa, as well as a friction force, Ff. Because it asks, what force is required? So that's kind of code for applied force, right? Now, do you remember doing like net force stuff, right? The F net, let's just, you know what, just watch for a second. Just watch, put your pencils down, just watch. F net is equal to MA, right? Okay, and F net. Now, the net horizontal is what I'm worried about. Cassie, you really need to watch. You got to stop that conversation because here's where the learning happens. F net, the x parts is only the FA plus the FF. The up and down don't have any effect on the acceleration, right? Because it's just sliding sideways, right?
Yes.
Okay, so which one of these things do I need to do first? I know the mass and I know the acceleration, right? So given my mass and acceleration, I can actually do that first, right? So okay, so let's do the blue one first. That's why I told you just to hold off there for a second. Okay, so the mass is 1600 and the acceleration is 1.2.
Wait, we can write it out.
Now you can write it, yeah. So 1600 times 1.2 is, of course, 1920. 1920 newtons. Now, everyone's first instinct is to automatically just subtract friction.
No, you can't.
Why not, Rada?
It's not in the same. You have to turn it to
I thought you were
newtons.
adding friction or something.
Right.
Oh, never mind.
Don't you always just subtract friction?
Nope.
But it's a negative. Well, I don't know.
The best bet is to not think about that and just to take what you figured out. F net is 1920. Take that and do what?
Turn it in.
Put it in the right spot. That's the net force. So that's going to be 1920. I'm solving for the FA. And my friction force is 200. Now, because it's friction, because it's opposite the FA, it's going to be minus 200.
Is friction always?
Yeah, as long as the applied force is positive. And now when that negative 200 goes to the other side, you actually get FA is going to be 1920 plus 200. I'm going to rewrite that again so you can read it.
Thanks, Mr. Bennett.
I aim to please. Which means that you're going to need an applied force of, you're going to add 200, 2120, right? Does that make sense? You need more applied force than the net force?
Yes.
Absolutely. The 200 of that 2120 goes towards the friction, right? Overcoming friction.
Yes.
You need more than is required because you're accelerating. Right? So I encourage you to write out these things, right? That's important. Right? When you write them out, it starts to make sense for you. Okay? Okay, let's try number 2. Everybody good with that one?
Okay, Bennett.
Let's see. All right, let's look at number 2. Object has a mass of 50 kilograms. It's at rest at the origin on a horizontal frictionless surface. Frictionless surface. At time t is equal to 0, a force of 10 newtons is applied to the object in the horizontal direction for 5 seconds. What are the position and velocity of the object at t is equal to 5 seconds? Okay, let me draw the picture. So I got a 50 kilogram object. Quite often we just put the mass inside the box like that. There's 10 newtons applied to the object. So the FA is 10. Do I have a weight force and normal force?
Yes.
I do. Do they have any effect here?
No.
Are they just going to clutter up our thinking?
Yes.
Possible. If you feel like you want them, you go ahead. I would say leave it up because it's not really, it's a horizontal question, right? Some profs would get upset about that because you're saying you're not being complete, but I think they're kind of like extra. Okay, and the time is 5 seconds. And the question is, what is the position, the velocity of the object at t is equal to 5 seconds? So how fast is it going after 5 seconds? How fast is it going? They're asking for the VF.
Yeah.
VF equals VI plus AT. The VI is 0. Right? Sitting at rest, VI is 0. Do I know the A? I don't know the A. Can I find the A? How can I find the A?
I don't know.
Bingo. The FA is the F net. How come? Because it's frictionless, right? That's the only one going sideways. So FA is equal to F net, which is equal to M times A.
And then we can find A like.
So the F net is our 50. Hang on, not 50. 10. Our mass is 50A. So now I'm going to subtract 50. Divide, thank you. Please don't make that mistake. Divide by 50. A is equal to 10 over 5, or 10 over 50, or 0.2, right? That'd be meters per second squared. Yeah. Do we need to worry about units sort of as we're going along the way? Some people get fired up about that. I'm not going to worry about it. I'm about the process. Okay, so the acceleration is 0.2. Now that I've got that, I can go VF equals VI plus AT. We're solving for the final velocity. The initial is 0. My acceleration is 0.2. And my time was 5 seconds. Oh, this is going to be easy. 0.2 times 5 is 1 meter per second. Oh, this number 2 is a little tricky. I still have to do the position at t is equal to 5 seconds. In other words, how far has it gone? I'm looking for the... Well, you could. I'm looking for the displacement, but don't I have like... I got like Vx squared equals Vx squared plus 2AD. I can use that one, can't I? Or D equals VIT plus a half AT squared. I can use that one too. Let's do that one. D equals VIT plus 1/2 AT squared.
And what are we trying to find?
Well, it asked me for the position and the velocity.
Oh.
Right?
Okay.
So I've got the velocity to find the position. I do this one because the D is out there. That's what I'm trying to find. The VIT is just going to be 0. 1/2 our acceleration, 0.2. How much time? 5 seconds. 5 squared. So you got to do the 5 squared first. So that's 25 times 0.2 times a half, right?
Oh, so you assume my child is
2.5? 2.5 meters is how far it's gone.
Holy crap.
Now, it's 2.5 meters. Let's read part B carefully here. I'm going to pause. I'm going to let you read part B carefully, and I want you to think about what that means. Is there? Is there? Okay.
The same force was applied.
Read part B. Talia, read part B and try to figure out what it means.
You have to add 5 seconds.
If the same force is again applied at t is equal to 15, what are the position and velocity of the object at 20 seconds? I'm feeling like I gotta sit here for this. No. Well, but it's what's the position?
It's still going. Yeah, I thought it meant like it gets another dollar.
Okay, so I'm going to draw the picture at these 5 second intervals, right? So 0, 5, 10, 15, and I guess there's one more, right? There's 20, which I don't have room for. Okay, so what's it doing between 0 and 5? It is accelerating at a rate of 0.2, right?
Yes.
And what is that distance, Tara, that we just figured out from 0 to 5?
2.5.
2.5 meters. What's happening between 5 and 10?
It's slowing down.
The same what?
Acceleration.
No, not the same acceleration, the same speed. So it's going here at 1 meter per second, and the next time that the force is applied is actually over here at 15, right?
Yes.
Let me just change this one here.
Get rid of 10.
Well, maybe I'll leave it there. So I'll just kind of make it small. Between here and here, how fast is it going?
It's the same. 1 meter per
1 meter per second. The whole time it's going 1 meter per second. For how long? 10 seconds, between 5 and 10. So 1 meter per second for 10 seconds. So this distance here is going to be 10 meters, right?
Yes.
And then you just add the little.
Right? Do you add just another 2.5?
No, yeah.
You have to
No.
Because exactly, because this 2.5 is based on the fact that the initial velocity is 0. Now between 15 and 20,
You have to do more math.
between 15 and 20, what is the acceleration? Is it still the same?
It's 0.2.
Still? How come?
Oh no, it'd be 0.4.
Is the acceleration still the same?
Oh.
I don't know.
Well, what's the force? The force says the same force, the same mass,
Oh, so it doesn't
Right?
change.
the acceleration is going to be 0.2. You might also want to say in here the acceleration is 0, right? Remember, 0 acceleration means that it's just moving at a constant speed. So is this still going to be 2.5? No, because as Brett pointed out, the VI is not 0. The VI is 1. So D equals VIT plus a half AT squared. This one's quite a bit trickier.
Let's not do this.
So this is going to be, my VI is 1. My time is 5. This 1/2 AT squared, 0.2, 5 squared. You guys work that out. Yep.
At least one more.
Okay.
Oh, I can't learn.
Just go. Especially if I'm
I hated the entire class.
busy with people, don't just, if I'm doing this, fine, ask, right? But if I'm running around, don't put your hand up for like 5 minutes waiting for me to say what. Just go. You're adults.
It's a minute.
A father is pulling his son out of a wagon. He pulls with 200 newtons of force at an angle of 25 above the horizontal. There is a 40 newtons of friction present. The boy and the wagon have, oh yes, I remember these. Okay, let's draw our FBD. Weight force, normal force, friction, and we've got an applied force, but it's at an angle. Right? Remember these? So FA is 200. The boy and the wagon have a mass of 35. And there's 40 newtons of friction present, like so. Okay, what do you feel like the first step should be?
Find
Find the X of the FA.
Find the X of the FA, okay. So remember we did this. We called this last year FAX, which is the X component of the applied force, just like we did with components. This is going to be FAY. The FAX, now this angle, do we have the angle? 25 degrees. I didn't write that in there. Is the FAX always going to be cos?
No.
Almost always. Because generally they give you this angle with respect to the horizontal. They very rarely say to the vertical. So most of the time it's going to be cos. So that's going to be FAX is going to be FA cos theta. Or remember all this coming back? 200
I'm crying now.
cos 25. That's where that went.
What?
200 times cos 25. 181.3.
Square root that.
181.3 is how much is actually pulling sideways. But what is the net force sideways? I have to also account for
The angle.
friction, right? No, this is the angle here. I've done the angle. So the F net, now really, you should be thinking about F net X, which just means the sum of all the X's, right? The sum of all the X's. It's just a label. So that's going to be FAX plus FF, right? So that's going to be my 181.3. And my friction force is going to be minus 40. So that's going to be, of course, 141.8. 0.3.
Doesn't matter.
Well, Coach Thacker says everything matters, right?
Hey, my coach knows.
Okay. Now, what else do I have to do here? I have to find out what is the acceleration. Oh, well, now I'm in good shape because it's going to be F net x is equal to ma. So 141.3. Okay, what about that FAY? It's going to matter real soon, but I already know what this friction force is. So I've already been, you would only worry about the FAY when you don't know what the friction force is, which you're going to see in the future. We're going to get there.
But it's not like F net, so it's like F net is
Yes, but, well, okay, so then I guess if that's F net x, then this is MA. Would this satisfy you, Megan, if I went put an x there? It's the x acceleration.
Okay, and that's what we're looking for.
Yes, because we're just worried, it's only going sideways, right? It's not going up and down. All the up and down is balanced. It's all zero.
Okay.
Does that satisfy you for now? Yeah.
Yes, I see those.
Okay, that's fine. It's a good question. 35AX.
No, I can't.
So the horizontal acceleration is going to be that number, and we're going to divide by 35, right?
Yep.
Wake up.
What? Oh. I was trying to get involved with the lesson.
4.04 meters per second squared. All right, I'm almost done. I got 10 minutes left. How far has the wagon traveled after 6 seconds? How far after 6 seconds? I'm looking for the distance. 6 seconds. I got the time. I got my acceleration. Hey, I can just do d equals VIT plus 1/2 AT squared. Right? So the VI is 0.
So lost.
1/2 acceleration, really?
I'll get it once I start doing it.
T squared is 6. Well, I'm trying to go slow enough that you can see what's going on, but I'm also keeping
What are
in
we
mind.
finding right now?
It asked, the question B was, how far has the wagon traveled after 6 seconds?
Okay.
How far? I'm solving for B.
Okay.
Solving for D, sorry. Right? So, 0.5 times 4.04 times 6 squared. 72.7?
Yep.
Okay? Here's what I'm going to do, because you are tired of me talking. I'm going to assign sample number 4 homework. 1,000 questions. One question. You can do it in the late 8 minutes or an hour, you can back up and take it home. But you've got to try example number 4 tomorrow.
Doing it before lunch.
Okay?
Tomorrow.
Here, I'll give you a hint. The coefficient of friction is mu, and the formula is FF over
Normal force.
Fn.
Yes.
Does that help? Does that help? The coefficient of friction is the mu value.
Dad's forgotten.
Right? Well, it gives you the coefficient of friction in the question.
Brain is shot. My brain's always shot. That's what makes it.
I think you're going to need it for the friction force. You should also remember that Fn, the normal force, is equal to the weight force, which is equal to m times g.